Right. So our second lesson in this unit will be covering the endocrine system. So in our previous lesson, we talked about the idea of homeostasis in the body and how there's mechanisms in place to help the body counteract any changes, and how this takes place through feedback system, both positive and negative feedback. We focused on the kidney and how that works to maintain our balance of different body fluids and waste products. We talked briefly, we just touched on hormones and how they play a major role in maintaining homeostasis in different areas of the bodies. And so today we are going to focus on the endocrine system of hormones and describe the effect that they have on various glands and cell types in the body, and how they control and keep the body under normal working conditions. So some of the things that you should keep in mind as we are going through our lesson is questions such as, how can hormones help the body to maintain these normal conditions that we are mentioning? And how can they also help the body to adapt to different stresses that are placed on the body? And also the male and the female reproductive hormones, what they do and how they work. And how finally can chemical substances like steroids improve the performance of athletes, and also what are their side effects and dangers. So in our endocrine system, we have a number of glands, and they produce chemical substances that are called hormones. And they act on different tissues in the body, and they bring about many different changes. It just simply depends on the role of the specific hormone and the specific organ, cell, or tissue that it acts upon. So these organs are only able to affect the cells that are designed to be affected, because those cells have got receptors on their membrane surfaces that the hormones can then bind to, can recognize and bind to, in order to gain entrance to the cell and bring about the change. And there's actually two main different groups of hormones. They're called steroid hormones and protein hormones. So these two groups here. Steroid hormones are cholesterol-based molecules, and those include the sex hormones, for example. And as they move towards their cell target, these hormones gain entry into the cytoplasm by recognizing and binding to their receptor. And once they form a complex with their receptor and move into the cell, then they move towards the nucleus, where they combine with the appropriate area on the DNA and prompt the transcription, followed by translation of relevant proteins. And then these proteins will bring about a change in the cell in some way to reestablish the homeostasis. And that's what we have demonstrated here in this left panel. This is an example of the mechanism in which steroid hormones act. And then on the right panel, we have an example of how protein hormones act. So these hormones are released from some sort of a cell that produces them. These contain chains of amino acids, hence they're proteins. These are often soluble in water, and they combine with the receptor. They attach themselves onto the receptor outside on the cell membrane. And sometimes they form this protein receptor complex, and the formation of this protein receptor complex then brings about the formation of a secondary messenger known as this cyclic AMP. So that once the hormone binds to its receptor, this hormone receptor complex then promotes the formation of cyclic AMP, which is a secondary message that then goes on to activate various other enzymes in the cytoplasm. And this cascade of enzyme action, from the binding of the hormone to the cell receptor to the activation of cyclic AMP and activation of the other enzymes, will give rise to then further products that will bring about the change in the cell to reestablish homeostasis. So these are two examples of two different types of hormones, steroid hormones and protein hormones. Now, our endocrine system has got 7 major glands, and these glands are responsible for producing hormones of the endocrine system that are shown here in this diagram. And each one of these glands, the hypothalamus, the pituitary, the thyroid, the parathyroid, the pancreas, and then the, there we go. The ovaries in the female, the testes in the male, as well as the kidneys and the adrenal glands. These glands we will take a look at and focus on the hormones that they produce and the tissues that these hormones that are produced by these glands will ultimately affect, and what will be the result of this hormonal action. Sometimes you have mechanisms in place that bring about homeostasis that don't just rely on the mechanism, on the action of a single hormone. They may require the action or a combination of a few different hormones in order to bring about and maintain that homeostasis and return the body to normal parameters. And sometimes this is what can make it difficult in medicine to try and establish and copy those responses within the body when systems aren't working properly through the use of various medications that affect hormonal changes, that this is quite a complex interaction. And if you have really any change to this system, any upset in the system, it can produce different disorders or diseases that will then need to be controlled. And again, these diagrams are from your Nelson textbook. You can also refer to your textbook to read up more about these endocrine glands and their hormones. So at the center, central really to all of these endocrine glands is the pituitary gland. And the pituitary gland is known as the master gland. And that is because it regulates the activity of many other endocrine glands. And it's located within the brain where it's connected to the hypothalamus. And let me just bring it so that we can talk about, sorry. There we go. Right. Right. So over here is a picture of the brain, and we have focused in on the area of the brain that contains the pituitary gland. The pituitary gland is this structure over here, and it's composed of 2 sections, the anterior pituitary and the posterior pituitary. It is connected to the hypothalamus gland here through this stalk region, and there's various nerve connections that establish communication between the pituitary and the hypothalamus. So the anterior portion of the pituitary, this produces and releases a number of hormones, while the posterior pituitary stores and releases a different set of hormones that are actually produced by the hypothalamus. The anterior pituitary is actually produces a total of 6 different hormones, and there is 4 of them that can act on other endocrine glands. And some examples of this are the thyroid stimulating hormone, TSH, I'll bolden that here, and that acts on the thyroid gland. When it acts on the thyroid gland, it stimulates it to do exactly what the name says. It's the thyroid stimulating hormone, and as such, it stimulates the thyroid to release the hormone thyroxine, which has an effect on metabolism. There's 2 other hormones that are also produced by the anterior pituitary. That is the follicle stimulating hormone, FSH, and LH. And these are also shown here in this picture, FSH and LH. I'll just highlight those as well for you. So FSH is the follicle stimulating hormone, and luteinizing hormone is LH. And these hormones, as you may guess from the names, act on the reproductive organs to stimulate the development and the ability for reproduction. There's another hormone called the adrenocorticotropic hormone, ATCH. And this hormone, it's also shown here, it stimulates it has an effect on the adrenal gland, more specifically on the adrenal cortex. And this produces then hormones in response to stress. There's other 2 hormones that act directly on target cells, causing change. This is the one is known as the growth hormone. Another name for the growth hormone is also somatotropin, and growth hormone, yeah, we've shown it over here in this diagram, and I'll highlight that. Growth hormone. And growth hormone really targets many different cells. The majority of the cells in the body respond to the growth hormone. It's particularly during the growth phase of development. And what it does, it spurts growth by increasing the intestinal absorption of calcium and increasing cell division and stimulating protein synthesis and lipid metabolism. So this hormone is critical during the growth stages of development. So 1, 2, 3, 4, 5, and 6. The 6th hormone is prolactin, and we're showing that here in this diagram. So here, prolactin is also produced by the anterior pituitary, and it stimulates the production of milk in the mammary glands. And the regulation of this hormone is quite unusual in that the hypothalamus will secrete a chemical transmitter called dopamine that will inhibit its production. But after birth, that's when you need the production of milk from the mammary glands. After birth, the stimulation of the nerve endings in the nipple during the feeding stimulates the production of prolactin and therefore stimulates milk production in the mammary glands. So that covers the anterior pituitary. And right behind it, we have the posterior pituitary. And the posterior pituitary stores and secretes different hormones. It's actually 2 hormones that it produces and secretes when it is signaled to do so by the hypothalamus. There is ADH, is one of them. ADH is the antidiuretic hormone that we discussed in our last lesson. And it helps to control that balance of water and salt levels in the kidney. It affects the tubule membranes to make them more or less permeable to water, if you remember. The second hormone that is produced by the posterior pituitary here is oxytocin. Oxytocin is the second hormone. And oxytocin has an important role in childbirth. And we also discussed this. This is the hormone that stimulates the muscles of the uterus to contract during labor. And it also acts on the mammary glands to produce milk, release of milk from the breasts. So those are the major hormones of the pituitary gland, both the anterior pituitary, which produces 6 different hormones that act on various tissues, and the posterior pituitary, which produces these 2 hormones and their respective tissues, the kidneys, the mammary glands, and the uterus for oxytocin. And in this section, this table, again, is a little summary of those hormones that we discussed, a summary of their target tissues, and what is the primary function of these hormones on these tissues. So now, hormones that affect metabolism are another important category of hormones. And there is really 3 endocrine glands that are involved with regulating metabolism within the body. One of them is the anterior pituitary, which we discussed, that produces the growth hormone, and that directly affects metabolism. Also, the thyroid gland is another one that helps to regulate, for example, the rate of glucose, at the rate at which glucose gets oxidized, and also the parathyroid gland. And the parathyroid gland regulates our calcium and phosphate levels. So let's just look a little bit more in detail at the thyroid, parathyroid gland over here that we haven't discussed yet. We already discussed the anterior pituitary and the growth hormone. So the thyroid gland, the thyroid gland, you'll find it at the base of your neck, right in front of the trachea, which is the windpipe. And we have a picture of it here. Yes, there. So this is the thyroid gland over here. Just zoom in on it for you right here. This bow tie shaped structure at the base of the neck, in front of the trachea, the windpipes. This is the thyroid gland. And then these little nodules, these 4 little nodules on the thyroid gland are called the parathyroids. All right. So now that we've had a look at it, let's go back to our table or back to our text. So we also talked about the thyroid hormone in that it releases this TSH, thyroid it is stimulated by the thyroid stimulating hormone. And when it is stimulated by the thyroid stimulating hormone, what the thyroid gland does, it releases the hormone thyroxine and triiodothyronine. And both of these hormones have iodine as a component. And so this is something important that we have to ingest in our diet in order for these hormones to be made and to function properly. These hormones' job is to increase the consumption of sugar by our cells and to increase energy production, especially in the muscles of the heart, in the skeletal muscles, in our liver, and in our kidney. And people who have high thyroxine levels, though they tend to have high glucose metabolism and also use up other nutrients more quickly when their levels of thyroxine is high. So they tend to be not to gain weight, and in even some extreme cases, this is called hyperthyroidism, where you're called hyperthyroid. That means your thyroid is working overtime, producing too much of this thyroxine. And if these thyroxine levels are too high, that's when your metabolism is often revved up, and your consumption of nutrients and glucose, and even your heart rate and your respiration, it's all elevated and increased. If, however, these thyroxine levels are low, then people tend to gain weight. They tend to have a sluggish more metabolism. It takes them longer to break down and metabolize their glucose in the blood. And so the excessive glucose that remains in the blood gets converted to fat. So people who are hypothyroid, actually I should highlight these two terms. People who are hypothyroid tend to put on weight and have a very slow metabolism and have very low energy. So the levels of these hormones are controlled through the negative feedback loop. And we discuss what and how a negative feedback loop works. A negative feedback loop works to actually, once that stimulus is present, it works to then inhibit that mechanism. And so it's a negative feedback. And so in this case, those receptors in the hypothalamus, and you remember hypothalamus is located just above the pituitary, those receptors have a recognition site for this hormone thyroxine. And so those receptors can recognize when these thyroxine levels have fallen low. And so what they will do in response to lower levels of thyroxine in the blood, they will secrete thyroid releasing hormone, which will then stimulate the pituitary to release the thyroid stimulating hormone, which then goes on and stimulates the thyroid to release more thyroxine. In that system, this is an example again of the negative feedback loop here. The thyroid gland also releases another hormone called calcitonin, and calcitonin is responsible to for mobilizing calcium stores from the blood into the bone tissue. And this hormone gets released when you have eaten a calcium-rich meal and when you're digesting it. So you have a lot of calcium, which has been absorbed by your intestine and is in circulation to your blood. So this hormone calcitonin then allows calcium from your blood to enter into your bone. And once it's in the bone, really that's the major site for the storage of calcium, is those skeletal bones of the body. And then this hormone works in concert with a hormone that is produced by the parathyroid gland. And the parathyroid gland is those 4 small glands that we talked about. I showed them to you. I pointed them out to you. They're located on the thyroid, embedded within the thyroid gland. And these glands, the parathyroid glands, help to maintain homeostasis by being responsive directly to chemical changes around them. For example, when calcium levels are low, the parathyroid glands release a hormone called parathyroid hormone, or PTH. And the effect of the release of this hormone is to raise calcium levels. And it does this by acting on the kidneys and the intestines and the bones. In the kidneys, it induces the kidneys to retain calcium while promoting calcium release from the bones. And the bone cells are signaled to break down, and calcium and phosphate separate. The calcium enters the blood, and the phosphate is excreted then in the urine. And also in the intestine, this hormone acts to bring calcium levels up by promoting better absorption of calcium from the food that is digested and is present in the intestine. And then once the calcium levels are back up to normal homeostasis levels, this parathyroid hormone is no longer released, again through a feedback mechanism. So calcitonin, which was one of the hormones that we mentioned that is released from the thyroid gland, we mentioned it over here. Together, this calcitonin and the parathyroid hormone, together, these two work in concert really to keep calcium levels in the blood at the proper level. And together, these two called antagonistic hormones because they work in opposite directions to each other, but working on the same substance in opposite directions, having opposite effects, and so they're called antagonistic hormones. And there's many antagonistic hormone system in place by the body, is used by the body to maintain balance. Again, what we just discussed is summarized in this table for the thyroid gland, the parathyroid, and the anterior pituitary, and the different hormones and their effect on how they affect metabolism. There are some homework questions that would be really useful for you to do. And then we talked about how hormones are also responsible for activating systems within the body in response to stress. So the hormones that respond to stress. And although there's many other glands involved too, it's actually the main hormone that is responsive to stress is the adrenal gland. And the adrenal gland is located on top of the kidney. If you remember back when we were talking about the kidney in our previous lesson, we talked about the word renal, renal artery, renal vein. Renal means having to do with the kidney, and so the adrenal glands are located right on top of the kidney. Let me see if I have a picture of it here. I'm pretty sure I do. Yeah, right here. We can zoom in a little bit. So there's the kidneys, and right on top of them, almost like a cap sitting on top, are the adrenal glands. So adrenal glands are made out of, or have two layers. One is their outer cortex, and then there's the inner medulla. And do I have a picture of that? Yes, I do, right here. So here you can see there's the adrenal medulla, and then there's the adrenal cortex, the outer layer over here. Sorry, this keeps jumping on me. So right, we're talking about the location of these. They're located on top of the kidney, and they have those two layers, the outer cortex and the inner medulla. And each of these layers acts quite independently of the other and provides different hormones depending on what is the situation and what is the response that's required. So the medulla portion releases hormones that provide quite a rapid, very fast, but short-lived. It only lasts for a very short duration. So rapid but short-lived response to stress, while the cortex portion provides a more sustained, slow, and longer lasting response. So that's really the major difference between those two portions of the adrenal gland. The medulla has a rapid but short-lived response. The cortex produces more sustained, longer lasting stress response. So let's look a little bit more closely at these two different sections. The adrenal cortex, first of all. So this portion produces a hormone called cortisol. And cortisol stimulates the synthesis of carbohydrates and also another hormone called aldosterone. And aldosterone's job is to regulate blood pressure. And we touched on this, I think, last lesson by altering that salt and water balance in the body. Both of these contribute to both cortisol and aldosterone. Both of them contribute to long-term stimulation of the immune system. Remember, hormones produced by the cortex, have that more sustained long-term stress response. So these have an effect, the long-term effect on stimulating the immune system in the case of stress, when there's stress on the body. And the release of these two hormones from the adrenal cortex, the release of cortisol and aldosterone, is controlled by that ACTH from the pituitary gland. So ACTH is produced by the pituitary gland, and its target is the adrenal cortex, and it leads to control of cortisol and aldosterone production. Now, looking at these two hormones, cortisol and aldosterone. So cortisol, first of all, what it does, it causes a large increase in the production of carbohydrates from amino acids and other substances. And so this increase in the conversion rate of organic molecules, such as amino acids and other organic molecules, into glucose leads to increased glycogen stores in the liver, and increased glycogen stores in the liver allows for a quick conversion of these stores back into glucose when the body suddenly needs it. It also stimulates the breakdown of lipids to be used as an alternate energy source, again, at the time of stress when the body needs it. It also inhibits metabolism and suppresses protein synthesis in the body, except in the brain and in the muscles, because those would be two organs that you would really need to have ready to go at the time of stress. Cortisol also has anti-inflammatory properties, in such that it helps to decrease the buildup of fluids in the tissues by decreasing the permeability of the blood vessels to fluids. So during stress, where you need more energy is available to focus on solving whatever is the problem that's causing the stress. And so by doing so, you slow down those cellular processes that are deemed non-essential. The hormone aldosterone, which is also produced by the adrenal cortex through the action of ACTH, it has an effect on the kidney, regulating water and salt levels. And in the kidney, as we discussed in last lesson too, it prompts the kidney to reabsorb more of the sodium, which causes in return more water to also be reabsorbed and retained. And in the case where you have more fluid, it also increases blood pressure. Now to look at the medulla of the adrenal gland. This portion of the gland then secretes also two types of hormones. These are very similar hormones, and these are called adrenaline, and the other name for adrenaline, it's also known as epinephrine. It also secretes noradrenaline, and the other name for noradrenaline is norepinephrine. So it stimulates, it secretes two hormones, adrenaline and noradrenaline, or also known as epinephrine and norepinephrine. And these are major hormones released in response to stress. I think everybody's heard the whole, when you're under stress, you have a release of adrenaline. And both of these act to increase heart rate and blood pressure and cause blood vessels to dilate in the heart and in the respiratory system. In the liver, they stimulate the breakdown of glycogen into glucose, and which results in an increased blood sugar levels. And all of this together in concert is the part of the flight or fight response to sudden, unexpected, stressful stimuli. And we sometimes, sometime or another, may have felt this response when we're suddenly or surprised, or suddenly feel like we're startled or in danger or scared. Our heart starts to pound, our breathing is increased, and also our awareness at that time is increased. We are hyper aware. So that is in response to the hormones of the adrenal medulla, the epinephrine and norepinephrine, increasing the release of glucose into our bloodstream and increasing our heart rate and dilating those blood vessels within our heart and our respiratory system, so that we can have this fight or flight response. And this fight or flight response has probably been something that, looking back evolutionary at our primitive ancestors, has probably helped them to survive when they've been in danger, when some prehistoric predator has been coming after them. But these mechanisms are there, and they have probably helped in the survival of our ancestors, and they work really well for a short-term response. But in the cases where you have somebody who has been subjected to long-term stress and is constantly under this production of epinephrine and noradrenaline in response to stress, when they're subjected to this type of long-term stress, it can be very detrimental to the overall health, and the body will just, in order to counteract this, the body will adjust to this type of perceived threat and just treats it as this being its new normal state, to constantly feel this constant long-term stress. But these conditions just lead to create more further long-term problems. And this is something that is observed more and more today as more people deal with stress within their day-to-day life, is that many people are under this type of long-term stress. And again, in this table, we have a summary of what we just discussed, the problems associated with being exposed to long-term stress is that you may have higher than normal blood sugar levels as a result of being under stress. You would have increased blood pressure from being stressed and also increased heart rate. And what possible problems can these lead to is that when you are constantly under a high blood sugar state, this affects the balance between blood and the extracellular fluids and leads to increased fluid uptake by the blood, and also, again, exacerbating that increased blood pressure, leading to possible kidney damage. And as a result of the kidney damage, increased water loss from the nephrons. The increased blood pressure can cause possible, sometimes if the blood pressure goes very high, it can lead to ruptures of blood vessels due to this higher blood pressure, and also lead to increased blood clotting. So again, all of these can be quite dangerous in the body. And also having an elevated heart rate, a constantly elevated heart rate can lead to this higher blood pressure, possibly stroke, possible destruction and damage to muscles of the heart, possibly leading to stroke and even heart attack. But there are other hormones that do change during stress, and those are involved in the regulation of blood sugar levels, and we'll discuss those in our next section as it comes up. So here in this diagram, again, we've summarized the involvement of the adrenal gland and how it responds to stress, a stressful situation, as is identified by your brain, be it a short-term stress or a long-term stress. In short-term stress, you have the cells within the hypothalamus sending signals to nerve cells in the spinal cord, and then these spinal cord cells stimulate those those cells in the adrenal medulla to secrete hormones. These adrenal medulla cells will secrete epinephrine and norepinephrine, and norepinephrine and epinephrine act to increase blood glucose levels from the glycogen that will be converted into glucose. They will act to increase heart rate, breathing rate, and also the rate of metabolism. They will also affect changes in the pattern of blood flow that direct more blood towards the heart and to the muscle cells, because if you can imagine, during a situation of sudden stress, during that fight and flight response, you may need to suddenly run away from this predator or burst into action. So you need to have quite a lot of blood flow to the heart and also to your muscle cells. However, in long-term stress response, suppose there is that long sustained stress response, you have the hypothalamus sends these types of releasing hormones towards the anterior lobe of the pituitary. And in the anterior lobe of the pituitary, you get secretion of ACTH, and ACTH gets carried by blood to the cells of this time in the adrenal cortex. And in the cortex, these cells will then secrete different types of glucocorticoids and mineral corticoids, which will then have their action in terms of glucocorticoids will lead to increase in blood glucose, because of proteins and fats that are being broken down and converted into glucose. And they will also suppress the inflammatory response of the immune system. The mineralocorticoids, they will increase the amount of sodium ions and water that's retained by the kidney and lead to an increase in blood volume and blood pressure as well. So we touched on how hormones can affect blood sugar levels. And really at the center of this is the pancreas. The pancreas is the organ responsible for secreting those hormones that help to maintain our blood sugar level around that all-important 0.1% level. And these hormones that are produced by the pancreas are actually produced by very specialized cells throughout the pancreas called the islets of Langerhans. And these cells produce two hormones, insulin and glucagon. And these, again, are antagonistic hormones, meaning that they act to counteract each other. When blood sugar levels are increased, which is usually what you have after you've had a meal, you have a release of insulin. And this insulin helps to promote, to change glucose into glycogen and causes the body's cells to become more permeable to glucose so that glucose can more easily enter the cells. And the effect of this, the effect of converting glucose to glycogen and increasing the permeability of cells to glucose, is that it moves glucose out of circulation, out of the blood, returning blood glucose levels back to normal. When levels of glucose are low, such as when you have missed a meal or need some energy or doing exercise, then you have the hormone glucagon, which will promote the conversion of glycogen back into glucose. And this allows the levels of glucose in the blood to be kept relatively stable. How these two hormones, insulin and glucagon, work in concert with each other in an antagonistic way. And also, the hormones adrenaline and noradrenaline, also known as epinephrine and norepinephrine, they also affect blood sugar levels by increasing the amount of glucose that is present in the blood. And also the hormone cortisol also helps to create more glucose, again, by promoting the conversion of different types of nutrient molecules, such as proteins and lipids, into glucose. So these hormones all together really help to control blood sugar levels, to keep them around the normal 0.1%, or to help to increase them in response to stress. And here in this table is a summary of the hormones that are involved in the control of blood sugar and where those hormones are located, and also what is the effect of those hormones. And we've discussed all of these in detail, but they're summarized for you in this table for your review. So this diagram shows the homeostasis of blood glucose levels, what we just discussed. And now we can go through it, bringing in all the different glands and the tissues that are involved. So if blood glucose levels, which are normally kept at around 0.1%, if they become higher than that, if you have more glucose in your blood than that, which is typically tends to happen after you've had a meal, you have blood sugar levels that are on the rise, then what this does is that it stimulates the release of insulin from the pancreas. And these are released from the cells called the islets of Langerhans in the pancreas. They release insulin into the blood. And what this does, insulin has got two targets. One, it targets the liver, where it converts glucose into glycogen. So glucose that's within the blood gets converted and stored into glycogen in the liver. But also it targets other cells within the body to make them more permeable to glucose, meaning that it permits more glucose to enter from the blood into these cells to be metabolized. And the result of both of these is that your glucose that was in the blood is now removed from the blood, and those blood glucose levels decrease and come back down to the normal level of its 0.1%. In contrast, when you have low blood glucose levels, such as after a period of fasting or exercise or some strenuous activity, you will then have the production of glucagon from the pancreas. This time, this is by the alpha cells of the islets of Langerhans. And they are released, this glucagon gets released into the blood. And what the action of glucagon is then to target the cells of the liver to convert that stored glycogen back into glucose, release it into the bloodstream. The effect of this is to increase blood glucose levels back up to normal levels and establish that homeostasis of blood glucose levels back at the 0.1% level. So now I'm just trying to see how we are doing for time. Oh, actually, we are doing okay for time. Now we can talk a little bit about, first of all, does anybody have any questions up until this point? Okay. So I can carry on then. So if everybody's okay with everything that I went through, now we can talk about the reproductive hormones. So these are the hormones that are responsible for reproduction in males and females. In both males and females, we produce both androgens, the male-associated hormones, and estrogens, the female-associated hormones. These are produced in both, but the difference is the amount of these types of hormones that are produced and the changes that they bring about in the body. As you can imagine, within females, there's a different level of, there are male-associated hormones, the androgens present, as well as the estrogens, but to different levels, and they target different tissues compared to what they may target in males and what level the androgens and the estrogens are in the male. So both of these hormones, these types of hormones, the male-associated hormones and the female-associated hormones, are produced by the adrenal cortex. In males, the androgens, or the male-associated hormones, are produced by the cortex, are quite negligible compared to the amount that is produced by the testes. So in males, there's both of these produced or both of these glands, both the adrenal cortex and the testes, both produce androgens, but to a much greater extent, these are produced by the testes in male, and to a lesser extent by the cortex, by the adrenal cortex. Let me just add that in just to be clear that we are still talking about adrenal cortex. Now contrast that to what you have in the females, but in the females, the adrenal cortex, again, I'm going to write adrenal cortex, that produces almost 50% of the androgen or the male-associated hormones that are produced in the female body. So in females, the major site for the production of androgens is the adrenal cortex, whereas in males, it is more the testes that produce the androgen hormones. Now, the estrogens, or the female-associated hormones that are produced here, become more important in females, especially after menopause. So after the menopause in females, when the ovaries really stop functioning and their function slows down, this is where the estrogens that are produced by the adrenal cortex take precedence and become more important. But at the time of puberty, there's a hormone called gonadotropin-releasing hormone, or GnRH. And this hormone that gets produced by the hypothalamus then goes to stimulate the pituitary gland to release both of these hormones, the follicle-stimulating hormone and the luteinizing hormone. And we talked about these earlier on, how they are released by the pituitary gland. In the pubescent male, the luteinizing hormone then goes to act on those interstitial cells, which will produce testosterone. The follicle-stimulating hormone acts on Sertoli cells that are responsible for sperm production. And once you have testosterone levels reached a certain target level, this then acts as a negative inhibitor and again signals the hypothalamus to slow down the release of gonadotropin-releasing hormone and stop stimulating the pituitary gland. Excuse me for one moment. I just have to, I'm really sorry for this interruption. I'll be all right, I'm terribly sorry for that. So where were we? Right, we were talking about in puberty in males, how the production of testosterone is stimulated by the luteinizing hormone, but once testosterone levels reach appropriate levels, then the testosterone will act as a negative inhibitor back at the hypothalamus and stopping the stimulation of the pituitary, which in turn stops the release of the luteinizing hormone, the follicle stimulating hormone. And so this acts as a negative inhibitor. And now the Sertoli cells, those are cells that are responsible for sperm production. Those also produce a substance called inhibin, and inhibin also acts as an inhibitor for the hypothalamus. So again, when testosterone levels then begin to drop somewhat, then the feedback loop is broken and the levels are stimulated to increase again. And this kind of control, this kind of inhibition and release occurs continuously in order to maintain proper levels of the hormone testosterone. And once the male reach puberty and become sexually mature, the sperm production will continually and constantly occur until for the rest of their lives. Testosterone that is produced at the beginning of puberty acts to influence the development of secondary characteristics in male. This includes the stimulating the development of sexual organs such as the penis and testes, and also increasing sex drive. It also helps to promote the development of facial hair and body hair and the growth of the larynx, the voice box, creating a deeper voice, and also helps to inhibit fat development and promote the formation of muscle. In the females, at the onset of puberty, pretty much starts the same way as in the males, where you have the gonadotropin releasing hormone from the hypothalamus, stimulating the release of follicle stimulating hormone and luteinizing hormone. Follicle stimulating hormone causes the follicle to grow. These are follicles on the ovaries where eggs are released, and the stimulation of the follicle, the growth of the follicle, releases the hormone estrogen. And estrogen, this stimulates the development of the lining of the uterus, the endometrium. And luteinizing hormone stimulates the development of the corpus luteum. And do I have a diagram of all of that here for you? No, but yeah, I'll try and actually get a diagram for this part of the text. This might be helpful. So yeah, you can check your notes later on. I will update these notes, and I think it might be helpful to have a diagram that shows all of this. So then luteinizing hormone, or LH, will stimulate the development of the corpus luteum. And the corpus luteum, if you guys remember from previous years biology class, is where once the follicle is released, it's that scar that is left behind on the ovary that becomes the corpus luteum, which also will release hormones. It will release estrogen, and so as these estrogen levels rise, they will also act as an inhibitor once they've reached the appropriate levels, and anything beyond that will act to inhibit and shut down the release of FSH, the follicle stimulating hormone, by the pituitary. Now, at the same time, the increase in these estrogen levels will stimulate the release of more luteinizing hormones. And as these levels increase, then you enter a cycle of ovulation. And the corpus luteum again is stimulated to release estrogen and release progesterone. And this further develops the lining of the endometrium. And as levels then increase, these will then act to inhibit both the follicle stimulating hormone and the luteinizing hormone. And in the case where there's been no fertilization, then the corpus luteum will eventually deteriorate and estrogen and progesterone levels will start to fall. And this will start the process of menstruation. And this is a cycle that continues to repeat itself from the onset of puberty all the way until menopause. And also, just as in males at the onset of puberty, in females at the beginning of puberty, these hormones really act to stimulate the production of secondary sex characteristics that are found in females, such as the development of breasts, such as the growth of hair around the pubic region, under the arms, the widening of the hips, and also the increase of body fat. And here in this chart, we've pretty much summarized what we just talked about. These feedback loops that we talked about, both in the male and in the female reproductive system. So if you can guess, this one is in the male, we have testes. This one is the case in females where we have ovaries and ovulation. So here is that negative feedback regulatory system in the males involving both FSH and LH. So again, the hypothalamus releases the hormone GnRH, or gonadotropin releasing hormone, which will then act on the anterior pituitary. And on the anterior pituitary, it acts to stimulate the release of these two hormones, FSH and LH. And FSH and LH then go on to affect the testes by stimulating the Sertoli cells of the testes to produce for sperm production, and also the interstitial cells to produce testosterone. The production of testosterone will further reinforce the production of sperm from the Sertoli cells, but it also acts as an inhibitor once the levels have reached high enough to go back and slow down the production of GnRH from the hypothalamus, slowing down the release of LH and FSH from the anterior pituitary, and slowing down the production of testosterone from the testes. So this acts as a negative inhibitor loop over here. The other negative inhibitor is the hormone inhibin, which will then act as a negative inhibitor on the action of the anterior pituitary and also on the hypothalamus. Again, the end result of both of these negative inhibitors, this negative feedback mechanism, is then to slow down the production of testosterone and also slow down the production of sperm. And this is how then the levels of testosterone are controlled in the male. Now, looking at the female, looking at the feedback loop that shows the regulation of these ovarian hormones. Okay. So again, starting with the, excuse me. Right, starting with the hypothalamus. Again, the hypothalamus produces this gonadotropin releasing hormone, which has the target anterior pituitary. It targets the anterior pituitary, and it stimulates the anterior pituitary to produce both FSH and LH. So up until this point, it's the same both in males and females. The hypothalamus produces GnRH. GnRH acts on anterior pituitary to produce both of these hormones, FSH and LH, both in males and females. Now, this is where it's different. It's because they target different organs. In the males, the target of these two hormones was the testes. In females, the target is the ovaries. And in the ovaries, the FSH acts on the growing follicle and which will lead to ovulation. It will also stimulate the growing follicle to release estrogen. And this increased estrogen that takes place at around mid-cycle stimulates further luteinizing hormone secretion. So it has sort of a positive feedback loop on the anterior pituitary, while this estrogen so this has to do with at which point in the cycle this happens. And once estrogen has reached high enough levels, it will go and have a negative effect on the anterior pituitary to slow down the production of these two hormones. Now, the other target for luteinizing hormone is to also target the corpus luteum. And from the corpus luteum, you have a release of progesterone and also some estrogen. And again, these will go and have a negative inhibitory effect on both the hypothalamus and also on the anterior pituitary. So up until this point is where you have similarity in both males and females, but beyond that, these target different organs which produce different hormones, testosterone in males, and from the ovaries, we have estrogen and progesterone in females. There's also some disorders having to do with the endocrine system. There's a great many disorders that affect human health, and we can really trace these back to improper hormonal function. And because, as we said, many of these hormones, and as we've seen in our examples that we've discussed, many of these hormones don't just have one function, one target, one effect. They have really multiple functions. It can sometimes be difficult to pinpoint exactly what is the cause of a disorder, but there are new treatments that are constantly being researched and found to overcome the symptoms of various disorders. And here in this table, we have an example of some of the more common disorders of the endocrine system. One of the ones that we are a little bit more familiar with, and we discussed somewhat in our last lesson, is diabetes. And here in this case, the affected endocrine gland is the pancreas. And the symptoms in diabetes is insufficient production of insulin, which will cause increased glucose levels in the blood and also in the urine. It also leads to the excretion of large volumes of urine and extreme thirst and lower energy. And oftentimes, if diabetes is left untreated, it can lead to kidney damage, nerve damage, blindness, and amputation of limbs due to dying tissue. There are other disorders. Another disorder of the thyroid gland is called goiter. And this is due to the lack of iodine. Remember, we said that the element iodine is very important to the functioning of the thyroid hormones, and lack of iodine causes the overstimulation of the thyroid, causing continuous growth, and the thyroid then enlarges as a result of this continual growth of the gland, creating a large swollen neck area. And we don't really see much of this disorder of goiter, especially definitely not in North America and Europe, because steps have been taken, and most of the salt, the table salt that we have access to nowadays, is iodized salt, and that is to combat goiter, to make sure that our diets have always got plenty of iodine in it, so that we don't suffer from this this problem of an enlarged, overactive thyroid. And then there's a few disorders of the pituitary gland. The first one is pituitary dwarfism. And in this case, there is insufficient growth hormone produced by the pituitary gland. And if you can imagine, insufficient growth hormone can lead to an abnormally short stature. And even prior to puberty, resulting in an abnormal growth of the long bones, and causing a very large stature, hence the name gigantism. There's also another disorder of the pituitary gland called acromegaly. And this is as a result of, again, excessive growth hormone produced in adulthood. And this results in a thickening of bone tissue, and can lead to a thickening of bone tissue of the head, the hands, the feet, and even spinal deformities. Then there's a couple of disorders, famously of the adrenal gland. One is Cushing's disease, and the other one is Addison's disease. In Cushing's disease, there is an excessive secretion of the hormone cortisol due to elevated amounts of ACTH, or sometimes as a result of an adrenal gland tumor, can also cause excessive secretion of cortisol from the adrenal gland. And what this does, it will cause high blood pressure, high blood glucose levels, muscle weakness, and the accumulation of fluid in tissues. And I think sometimes some patients who have Cushing's disease often look like they might be there might be some swelling in them due to the accumulation of fluids. In Addison's disease, there is insufficient, not excessive as in the case of Cushing's disease, but insufficient amounts of cortisol and aldosterone. And what this does, it causes low blood pressure, low blood sugar, some weight loss, and muscle weakness in Addison's disease. So these are some examples of disorders of the endocrine system and the various glands and hormones that are involved. I think, nope, this does not bring us to the end of our lesson. Thankfully, we still have half an hour, and we can talk about performance enhancing drugs. So we talked about this at the beginning of the lesson. We were going to talk about steroids and performance enhancing drugs. And so historically, people have experimented with many different natural substances to look at the effect that they might have on the human body. Certainly, caffeine is one famous one that is found to mimic adrenaline somewhat, raising heart rate, raising blood pressure, increasing alertness. But also in sports competition, in the 50s, anabolic steroids were introduced and used by weightlifters. And these anabolic steroids do a good job of mimicking the hormone testosterone, and testosterone naturally stimulates the body to have reduced fat storage and to build muscles. These are anabolic steroids, and the word anabolic means growing or building. So I think we've talked about anabolic pathways previously in this course, anabolic versus catabolic. So anabolic means growing or building. And these steroids have been found to increase muscle mass and reduce body fat, increase strength, and improve endurance. And for athletes in sports that require these short bursts of strength and energy, it has the result of giving them a certain edge, a certain advantage. And some athletes claim that using steroids will also help them to recover from injury at a faster rate that allows them to train more rigorously. Steroid users typically use steroid levels that are quite high, that are sometimes in the order of 10 to sometimes tens of thousands times higher than any dose that might be prescribed in a doctor for some medical purpose. And as you might imagine, there's a certain amount of risks associated with these kinds of doses, risks that will affect the long-term health, especially if there is extended use of these drugs for a long time. This is particularly dangerous and of concern in younger individuals who have not yet finished fully growing. Steroids can cause premature fusing of those growth plates in long bones of the body, which can reduce their potential height. They might have shorter stature as a result of steroid use. And some people can also experience mood swings or uncontrollable rage. And on a more physical level, altering these levels of sex hormones can affect secondary sexual characteristics. So in both males and in females, there might be increased production of acne, bad breath, high blood pressure, liver disease, kidney disease, and even may lead to certain types of cancers. Steroid use in males may result in premature baldness or shrinking testes and reduced sperm count, and sometimes even the development of breasts. In females, females can develop facial hair, have a reduction in breast tissue, and experience changes or even the cessation, the ending of their menstrual cycle, their reproductive cycle. In 1980s, there was a famous story where that's where I think steroids were at their height of being used, where we had that Canadian athlete, Ben Johnson, who got stripped of his gold medal in that 100-meter race when he ended up testing positive for being on anabolic steroids. And since then, drugs that are available to improve performance have become much more extensive and far-ranging and certainly more sophisticated. There's certain beta blockers that are used by archers or sharpshooters to help them slow their heart rate down to reduce their nervousness and make them more calm so that they can calmly hit their target. For endurance athletes, some use drugs such as erythropoietin, which helps to boost red blood cell production and allows them to have increased transport of oxygen to their tissue. And so if you have more oxygen, obviously you have more energy. But today, the International Olympic Committee lists over, I'm sure this number is actually probably greater than this now if I were to check, a great number of steroids and their related compounds that are banned for use by athletes. And every winning athlete gets now tested for the presence of these banned substances in their blood and urine. But as these tests, if you can imagine, improve to be able to detect these substances better, as you can imagine, there's also developments in ways to mask the presence of these substances. And oftentimes they might not work, and it leads to quite a lot of disgrace and taking away of medals. So this is certainly something that has been a hot topic in sports and in Olympics in particular. Here's a list of, it's certainly not a complete list, but a representation of some of the banned performance enhancing drugs. And some of these are anabolic steroids. Some of these fall under the category of peptide hormones, beta blockers, and other stimulants. And also their advantages and the advantage that they might give athletes who might be using these substances, but also there's quite an extensive list of side effects associated with the use of these types of drugs. And so because there's quite a bit of sophisticated scientific method behind these drugs, it might be difficult for drug testing programs to stay on top of all the new medications and all the new performance enhancing drugs that are constantly being developed. And you can imagine that in various Olympic events, sometimes they hang on to the samples that are provided by athletes, are kept for quite some time, many years, sometimes after the event, just in case new techniques or methods, new tests are developed to be able to detect more and more banned substances. And so therefore they might periodically be checking some of these old stored samples for the presence of any illegal performance enhancing drugs within. All right, so that brings us to the end of our current lesson. Next Monday, we'll carry on with lesson 15 on the nervous system. And after that, we will have lesson 16 on the immune system. Okay. So if there's no further questions, I can stop recording and I can end our lesson here.